Hello guys, Massimo here, welcome back. It's time to see our BigO part 3. And please, if you like my channel and my videos, subscribe to my channel, like and share my videos. Okay, enjoy it. It's time to deep dive on the analysis of algorithms, the BigO part 3. All we want to know is efficiency. And in order to do that, we need to calculate time and space. How much time or how long does it take for our algorithm to run, and how much space we are using to run that algorithm against that input. I brought here as a first example the printing all elements, which is a very simple algorithm. My input is an integer array which has these elements, and it also has the size of 20. So my n, or my input size, is 20. I'm simply going over all elements here and printing one by one. That's it. I'm iterating n times, and for each one of them I'm executing a simple operation, as we've seen before. In spite of the fact the for is not a simple operation, it's complex, but I'm simply going through n times and printing one by one. Then the whole work lies on printing the elements, which is done one step at a time. I have my for loop, and the green arrow indicates where I'm doing the actual work, the interesting thing. So my time complexity is O of n, because I'm going through all n elements, and my space is O of 1, as I am not using any extra space. The second example here is similar to the first one, which is the brute force search. I have the same array, the same elements, the same size, but now I have a target element, which is a target value that I want to see if my input array has that element. If so, I simply print the position. That's all what it does. As you can see here, the algorithm is almost the same. The only difference here is instead of simply printing the value, I'm doing a comparison in order to check if I found my target or not. If I found it, so I simply print the position. Here I'm going n times, I'm going over n elements, and I'm doing a simple step here, which is a comparison, just to check if I can find my target. If I do, I print its position. So I'm going over n times, iterating n times, and I'm doing one operation or one step per element, which gives me time complexity of O of n and space complexity O of 1, as I'm not using any extra space to process my algorithm over that data set. Another interesting example is duplicating an array. That's exactly the same array as before, but now what I'm doing is I want to copy or clone. In this case, I'm copying the elements from A to B. I'm creating a new array here, and I'll copy over all elements from A to B. In order to do that, again, I have to go over n elements, as I want to copy all of them. And for each element in A, I copied it over to B. Again, I'm going n times, as you can see here. And I'm copying every single element from A to B. Then my time complexity is O of n, because I have to go n times. And my space complexity is O of n as well, because I'm simply copying all elements from A, and I'm creating a copy into B. So I'm duplicating my input. That's why I'm using this extra space. Another interesting fact is we can sum the running time. I have this other example here. I have two arrays, m and n. I go over m on all elements and I print element by element. After that, I do the same thing to n. I print all elements of n. Then I have here O of m because I have to go over all elements of m, and for each element I'm doing a simple operation which is printing, and I do the same thing to the other array n. I go over it n times, so from start to end, and I also print every single element. So I have two for loops, but in two separate steps. So my time complexity is O of m plus n, because my algorithm is the whole method main, which comprises going over m. After that, I go over n. And space complexity O of 1, because I'm not using any extra space. Another example here is that we can multiply the running time. I brought here the same arrays, but this time what I'm doing is I want to print all pairs. So 13.9, 13.8, 13.10, and so on. 5.9, 5.8, 5.10, and on. That's why I have these two nested for loops here, because for every element on m, I go over n times to print the pairs. So I have two for loops here, but this time they're nested, and I'm running over two different inputs, m and n, which gives me a time complexity O m times n, because for every element in m, I go n times on the array n. And my space complexity is O of 1, because I'm doing a simple operation and I'm not using any extra space. Another interesting example is the insertion sort algorithm. It's a sorting algorithm, and we will have a complete session for that later, for searching and sorting. But just to quickly illustrate another running time here, I have a single input, which is my array of integers, which is called a. Then I go over it n times on this outer loop, but I also have to do almost the same thing here in the inner loop, because I need to compare after the first element, I need to compare that element with the previous one to check if it's less than the previous one, because I have to swap them in order to sort. I have this nested loop here, but as you can see, I'm doing this nested loop over this same input, which is the same array A, because I need to swap the elements. And I'm doing here n times, then here I do n times minus 1 or minus 2 and until I get to the end of the array. So I have the first 4 here, I have the second 4 here, which they are nested and they operate over the same input. So my time complexity is O of n squared, and space complexity is O of 1. We don't have to worry too much about insertion sort, because we are going to see many sorting algorithms on the search and sorting section. There is another interesting problem here, which is the triple sum. As we have an input and we want to sum all the triplets. So that's going to be element 0 plus 1 plus 2 and element 1 plus 2 plus 3 and so on until we get to the end of the array. Then we have to operate over the same array, and I need 3 nested loops. I have the first one here, second one here, which is I plus 1, see, I and I plus 1, and the third one here is j plus 1, which is the previous one. Then I'm going over and I'm moving my pointer one by one. First element, second element, third element. Three nested fors, they operate over the same input. My time complexity is O n cubic, and space complexity O of 1, because I'm simply doing a summation here, which is a simple step. For logarithmic runtimes, we saw that quickly previously. A good example is the binary search, which runs in O log n. We're gonna see more on binary search in the search and sort section. But quickly, it simply compares the target value to a middle element in the array, and keep doing the same thing on the left or the right, depending on the values. It simply keep dividing the array by 2 until it gets to 1. That's why we get a logarithmic runtime. As this example here, if my n is equals to 8, so 8 over 2 equals to 4, 4 over 2 equals 2, 2 over 2 equals to 1. Then my log 2 of 8 is equals 3. We're gonna see more about logs on the binary search in the search and sorting. Another thing is space for recursion. The next section is about recursion. You don't have to worry too much about it. We're gonna have a lot to talk about on the next section. But just to give you a quick taste, recursion takes extra space because it uses a call stack to manipulate the values. Then we're gonna use extra space. Even if you are doing the work on a linear time, we'll be using an extra space. As you can see here, I'm simply calling a non-recursive multiply, which is simply 2 times 3. That's pretty straightforward. But I can also make a multiply method which uses recursion to give me the value I want. So basically, I'm given a base number, which is 2, and how much times or any times it's going to sum that number in order to get me the result I want. So we keep going on that recursion, summing the base number plus the result of the next recursion. So time complexity is O of n, and space complexity O of n, because it needs to go until times equals to 0, and then it returns. More on recursion on the next section. And folks, this is the end of the BigO. I hope you guys have enjoyed. I did. So see you guys on the next one.